Hello everyone, welcome to online video lecture series developed by Jawaharlal Nehru Technological University Kakinada in association with Andhra Pradesh State Council of Higher Education. This is Dr. M. Prem Kumar, working as professor in the Department of Electronics and Communication Engineering, Sri Vishnu Engineering College for Women, Bhimavaram. Welcome to online lecture series. In today's lecture, I am going to discuss about filter characteristics of linear systems. Consider an LTI system, continuous time LTI system. LTI system means it should satisfy the two properties, linearity property and the time invariant property. Normal system input is x of t and this is some transformation. This is nothing but transformation of input x of t. So coming to the LTI system, this is continuous time LTI system. Input is x of t is y of t, which is nothing but the convolution between x of t and h of t. So impulse response of this LTI system is h of t. Once you know the impulse response, whatever may be the input signal x of t, we can simply convolving x of t with h of t. Now apply Fourier transforms on both sides. So x of t Fourier transform is x of j omega and h of t Fourier transform is h of j omega and y of t Fourier transform is y of j omega, which is equal to, here is the convolution between x of t and h of t. So convolution in one domain is nothing but multiplication in another domain. So x of j omega of j omega. So in the previous chapter you might have studied about the convolution property of Fourier transform. In that, convolution in time domain is nothing but multiplication in frequency domain. Vice versa. Of t convolution with h of t give x of j omega into h of j omega. Similarly, when we multiply x of t into h of t, we should get to h of j omega and h of j omega. This is now, so you will see output y of j omega is equal to x of j omega into h of j omega. So h of j omega is nothing but h of j omega is nothing but output frequency response of transfer function or the frequency response of LTI system. Now if you observe, depends upon the input signal, something is multiplied, that is h of e power j, h of j omega is multiplied to get the output of y of j omega. So far LTI system, continuous time LTI system. Now if you observe in the frequency domain, this LTI system can be used as a filter, filter. We will see how that can be used as a filter. So output x of j omega into h of j omega is equal to y of j omega. So based on the characteristics of h of j omega, some of the frequency components of the input signal may not present at the output of the system. Suppose h of j omega is a low pass filter. Suppose filter exhibits a low pass characteristic. So this is x of e power j omega. X of j omega will have all frequency components. All frequency components. After multiplying this with a low pass filter, output y of j omega will have only the low frequency components. Why? Because all frequency components are multiplied with low frequency components of this, and all other high frequency components will be blocked. So if we in terms of polar form, so y of j omega can be written as mod y of j omega into angle of y of j omega. So similarly, x of j omega will be equal to mod x of j omega j angle of x of j omega. Similarly, h of j omega is equal to, so this is mod h of j omega modulus into h of j omega. If you substitute these three in the above equation, so j omega mod e power j angle of j omega, this is angle of y of j equal to x of j omega mod to of j x of j omega into h of j omega mod into e power angle of h of j omega. So if you compare this, mod y of j omega is equal to x of j omega into mod h of j omega. And similarly, if you consider the angle of y of j omega equal to angle of x of j omega plus angle of h of j omega. So mod x of j omega is nothing but the magnitude spectrum of the input. This magnitude spectrum of the input has been changed to mod x of j omega into mod h of j omega. And mod of h of j omega is multiplied by mod of x of j omega. That is with respect to the magnitude response of the output. Now coming to the phase response of the input has been changed to plus h of mod h of j omega, angle h of j omega. So output phase must be equal to input phase plus phase of the transfer function. And mod of j omega, this is nothing but magnitude spectrum. Magnitude spectrum. This is angle of j omega is nothing but phase spectrum. Magnitude spectrum has been changed to mod x of j omega into mod h of j omega. Input phase spectrum has been changed to angle of x of j omega has been added to angle of h of j omega. So from these two, magnitude spectrum and phase spectrum, the frequency has been changed. That's why this h of j omega is represented as the frequency response. And for this reason, h of j omega is called the frequency response of the system. When the input signal is passed through the system acts as a filter which may boost certain frequency components and attenuates some other depending upon the nature of h of j omega. And it also changes the relative phases of various frequency components. Suppose h of j omega is a low pass filter. Suppose this is a low pass filter. So input x of j omega is having all frequency components. So output will have only the low frequency components because this is multiplied by h of j omega. So in this case, h of j omega can be treated as a filter, treated as a filter. Suppose x h of j omega is a high pass filter. H of j omega is a high pass filter, which means higher frequency components is passed through the filter and lower frequency components below the cutoff frequency will be blocked. So y of j omega will have only the higher frequency components. In this way, so h of j omega can be treated as a filter. So depends upon the characteristics of h of j omega. H of j omega can be treated as a filter.